hear the sound coming from both ways. Good morning everyone. My name is Robin Biju Thomas. You'll see this thomasrob.in as my website. If you want to connect with me, you can check that. That's a constant in all of those slides there. How many of you here are familiar with IoT? Okay, that's a lot more than I expected. So the last time I gave an IoT talk at a slightly generic crowd meetup, I went into a lot of depth of IoT testing and people were getting a bit bored, so I made it a bit abstract. But again, the talk was pretty much prepared for just over 30 minutes, 45 minutes, so we'll have plenty of time for discussion, and the crowd today seems to be quite engaging. We had a lot of great discussions during the last talk, so feel free to interrupt me at any point of time, and we can go into more details and depth as necessary. So, quick introduction. As I mentioned, I work in a startup called IOTify. We are into IoT testing, stateful simulation of devices. Not going into a lot of depth there today, but being a startup, you wear a lot of hats. The one that I like is technical architect. That's what I put there, but I handle a lot in terms of solutions architecture. Basically, you are given a problem, find a solution for it. So everything from Kubernetes deployments, and I see a few familiar faces from Kubernetes community days that happened last weekend. So, and as also is mentioned here, I'm a generalist, or you can consider deep stack, basically troubleshooting. Some problems involve you working from C# or to Bash to JavaScript to Vue.js in the same debugging scenario. At the same time deploying in ECS, EKS, all of that. So it forms a lot of roles of an integration engineer. You kind of do what is necessary. So deep stack is a buzzword that I found very interesting. So IoT, for the few that are not quite familiar with it, also my presentation will not have a lot of useful information, it's just visual aids. I prefer communicating or engaging with the crowd more. There's not going to be a lot to read here. So IoT, for those who are not familiar with that field, is basically what you see here is the fridge reminding you to not forget to buy milk. So as funny as that is, you can think of the tech involved in making that happen. This is not just a joke, this is a reality right now. If you Samsung Opera House, at Samsung Opera House, if you basically go, you'll see fridges that have cameras inside them. So you can see what's inside the fridge without even opening the fridge. It also has object detection and recognition to understand what the level of milk or whatever groceries that you have is. It also does an inventory system, so when you buy fresh produce, it updates the inventory of whatever is available for you, right? And it does suggestions in terms of recipes that you can do when you need to replenish that, even integrate with Alexa as necessary. Is the audio fine? Yes. So yeah, you automatically place orders as necessary. All of that is possible. But like, really think of the tech that's happening. There is a camera or there is a sensor of some sort within your fridge that's doing some object detection. It's doing some classification. It sends data to a remote server. It's as debatable as the privacy or whatever considerations there are. That's one way to do it. And there's some business logic that's going on, and then some actuation or some implementation or some action gets taken place with that information, right? So that's basically what IoT is, and it can be anything these days. Easiest thing is a smart light. So your Wipro, Cisco lights that you can control with your phones. That's how it all started, and now we are in this crazy mess where if you want to get anything to work, you need to have like a dozen apps on your phone. So it's a slippery slope about what you can enable with IoT and where you should pretty much draw the lines there. So in pursuit of convenience, we might end up creating something super inconvenient. and there are business considerations. For example, like in the previous slide, there was a block of politics that was intentionally left out. Right? Similarly, there are business interests that often factor into whatever architecture or whatever we are going to talk about today, that we are not, like from an idealistic point of view, we do not consider as much. So IoT really was the buzzword. For example, right now generative AI is your go-to keyword, right? Everywhere, even today there are at least 2 generative AI meetups happening in Bangalore. And wherever you go, for example, if you want promotions or whatever, you implement generative AI into your infrastructure, and that's sort of the business requirement. So IoT was in such a stage in 2000, let's say 12 to 15, you can say, when it was the buzzword. You're connecting everything to IoT, and every engineer is trying to enable some IoT application or IoT features into their existing product. So that's where the infancy of the technology is. So your toaster or your coffee machine making coffee right as you wake up, or your car basically telling you what the nearest gas tank is or a refueling station is as your tank levels get depleted. So applications are endless. Again, you have to sort of think of this slippery slope, right? For example, NFTs. How many of you know what NFT is? Non-fungible tokens. A lot of people, if you open your Google News feed, probably September, October of last year, it was at its peak, right? You can't open Google News without coming across the term NFT. And how many of you think NFT is a joke, or right? I personally think the technology is quite inspiring. I personally think that blockchain and NFT had a lot of potential. It just got completely sidelined in this gimmick of art or tokenizations or whatever that happened, and a lot of the scams that happened, and technology got sidelined there, right? And it was also in its infancy. Similarly, IoT had such crazy adoptions where even where it did not make sense, people were just connecting things to IoT. There were a lot of issues that happened in terms of privacy, data breaches, cases where IoT security was also in its infancy. So unfederated access to your home security cameras, things like that were genuine concerns. All of that happened. So this I guess is about 2015. Yeah, as of July 2015. And IoT is right at its peak over here. So fast forward to, let's say, 2017, you can see IoT as such, it's a bit blurred, but IoT as such, it's in and of itself is not there here. IoT pretty much got broken up. You can see IoT platforms coming up here. You can see digital twins somewhere here. So IoT as the topic is quite vast. So just to enable these communications or these features that we said, it is quite difficult to just have all of that under one stack, right? Even if you consider in terms of an engineer, there has to be electronics engineers. You need your VLSI guys for low-level chip design that's very power efficient, and those kinds of design constraints and criteria that you have to factor in. You need telecommunication engineers for physical layers. You need systems engineers for data ingress. You need ML engineers for processing and analytics. So it's generally not the case that one technology that you see on one of these charts stays intact. As it gets more matured, it gets broken up into different components. So that's sort of what you see here happening around 2017. By the way, is there anybody here who does not know what this chart is, the Gartner hype cycle?
I don't know.
Okay, so Gartner is a consultancy company, but every year they basically put out this report called, or rather this chart called the Gartner hype cycle. And it's a very controversies or radical opinions aside, it's a good way to see where new and upcoming technologies are in terms of adoption. So you have your basic stages like innovation trigger, peak of inflated expectation. I think the laser isn't working. So you have that first initial rocket launch stage where it's innovation trigger. So there a lot of engineers are doing a lot of cool stuff and basically ramping up the technology to its peak potential. This is when it starts to get its market awareness and people start noticing it. Then let's say slightly more business centric guys kick in looking for the next big thing, and then they try to put that technology into everything. So eventually the technology reaches the peak of inflated expectations. I can't seem to talk today for some reason. And then there's a very steep fall. So for example, I think I haven't checked the latest hype cycle for where NFTs are, but right now it's a bit of radio silence in terms of NFTs, right? that's sort of that downfall. And then eventually I still have hope that realistic applications of that technology will come up. That's this slope of enlightenment and then plateau of productivity. So it basically shows the evolution of a technology from pure hype, wherein it's the good hype that fuels a lot of innovation, then that inflation stage where it's taken beyond what it's meant to be, that fall that happens successively where reality kicks in, and then eventually it finds a good product market fit where it's actually practical. So IoT, like I mentioned earlier, it was here around 2015-ish. Then it started falling, and other components of IoT kind of got broken up, and then it's reaching a maturity phase. And I guess in 2022, the start isn't fully fleshed out, but IoT is. Oh, you can see NFTs there. You can see IoT is. Several components of IoT would be somewhere along the second half of this. As in, enterprise and businesses, like serious businesses, are adopting things and creating real life applications of it. So I met somebody earlier today who was working on logistics and last mile connectivity, your sensors, for example, what Samsung's doing. All of these, whenever it's enterprise-centric stuff, you need stability and practicality and business outcomes, right? It can't be just for the sake of it. So yeah, that's basically what happened with IoT. That's a summary. It was sort of in its peak in 2012, 2015. It went through that trough of disillusionment, and now it's, in my opinion, or the trends that you're seeing, it's essentially in realistic adoption, and it has a good amount of market penetration because of the insights that it can have, right? You're dealing with electric cars, your electric scooters, Ather for example. You can do a lot of predictive maintenance stuff. For example, if you have server racks or data center infrastructure, you can monitor how the temperature variations are happening. You know the optimum temperature for the silicon beyond which it might start long-term degradation. So for example, if you take AWS data centers or if you take real super huge data centers, the long-time life matters quite a bit, right? When you're talking about your gaming PC, it's all about the gigahertz. Let's say how can it cross 3 gigahertz, 4 gigahertz. But server components generally don't get pushed that far because sustainability matters, your power requirements matter, the life of the component matters. You can't just keep churning through hardware, right? So you try to optimize the, let's say, operating temperature versus the performance. So all of that involves a lot of data acquisition, a lot of telemetry. Even Ather, I think they have this predictive maintenance of batteries, like battery replacement, their battery warranties, all of that. Basically, you can get a call from your service center before the problem in your vehicle escalates to a real actual problem, right? Again, you can argue about the privacy concerns or that, But I think that's quite an interesting application of it. So if you're a couple of my juniors in college, they worked on this predictive maintenance system wherein they were listening to the sound of machines, the sound that machines were making. So like a lathe, for example, in mechanical engineering, lathe is something that you use to fabricate cylindrical or things with a circular cross section. So those have a lot of gears and stuff. So if those gears are misaligned, abrasion can happen. And by the time a human really notices what's going wrong there, that abrasion might have gone too far. If it's at an early stage, you can just correct the alignment and things would have been fine. So what they were trying to do was basically take sound samples and then run it through an ML filter, try to find differences between normal operation and abnormal operation, and then send out notifications to maintenance engineers. Same thing applies to your cars, your scooters, whatever it is, right? So those are some of the real practical applications of IoT that can happen. So basically, as we are going through this adoption, people are sort of finding focus areas. Now, most of the, let's say, engineers that are graduating sort of go into that orthodox stream of typical system architecture, right? You find either you go into data engineering or you go into, say, application development, things like that. People are still finding their way around IoT development. So again, telemetry, data ingest, all of those are different components under this. So these concepts might find its way into something or the other that you are actually working on that can be extended to this in some capacity. So the title of the talk is Challenges in Architecting IoT Systems. But so let's just take a very quick overview of what a traditional software systems. The talk before this was incredibly exhaustive of all of the design and architectural considerations that you can make in terms of microservices. I do not aim to go that far into detail, and definitely I cannot surpass what was already presented here. That was amazing. So this is just something that I put together. This is probably the most generic system architecture that you can find here. Probably any company in its infancy, probably startups here or small to medium businesses that have some kind of a web application presence might follow something along these lines. So you have your client, that can be a phone, that can be your browser, whatever, communicating over HTTP. You have a load balancer or your API gateway that looks for access restrictions. You have your messaging bus, say Kafka, NATS, whatever it is, internal communication. You have microservices here. That's what I'm familiar with, so I have a bias to that. That's why I represented it as microservices there. Databases connected to each service, and that's your generic system here, right? If you want to say bring up like come out with a new startup, this is probably the infrastructure that you would go with. Maybe not split into services, but again we are going into that microservices versus monoliths discussion. Let's stay on topic in terms of IoT systems. So IoT systems, again, so this classification methodology, this is the most prevalent one that you can come across. Either you can see a 3-layer or a 5-layer architecture. Both are fundamentally the same. It's like on how much granularity that you want to go. So first layer in both cases is perception. So perception is sensing. So let's consider agricultural IoT. So a lot of farmers, they have that innate feel on how much moisture that the soil needs, right? But being engineers, we try to quantify that. So let's say a soil moisture sensor. It's quite, I'm sure everyone here is from a science background, so, and pardon me if I tend to jump around into electronics now and then. So a soil moisture sensor is quite simple. There are 2 probes that stick into the soil, and water in its purest form is not conductive, but with all the minerals in the soil, there will be some amount of current that goes through it. So it essentially, the sensor essentially measures the current that flows through the soil, and comes up with an analog range of values, right? So this is the electronics end of things. Now we need to take this all the way to the cloud. So let's look at certain like how that goes through. So that lowest block of device can be called perception. What is perception? Your understanding of the environment. That's why I put sensing in brackets. Perception or sensing. You'll see perception in the diagrams. I prefer sensing. So you can consider this soil moisture sensor. So that's basically two wires connected to the ground, connected to an amplifier circuit. That's it. But now this needs network access. It needs to connect to a computer of some capacity. It needs to send it to some endpoint. So you use a microcontroller there. Now in a field, these can be spread across acres, right? So you can't have one computer that's entirely Ethernet enabled. You can't have like an Intel Atom processor or something of that computing caliber spread out through the fields. You have to run wiring, all of that, not practical, right? So there is a transport layer that comes next. So this can handle, this varies quite a bit in terms of application. One of the most popular things in this agricultural sector is called LoRa, abbreviation of long range, that uses megahertz range of radio waves essentially. So even in your mobile phone you might see 2.4 gigahertz, 2.4 and 5, those are gigahertz range. Your FM is 91.9 or whatever megahertz. So just putting things into perspective, this is around 433 megahertz is what LoRa runs on. If you want something in your home, so your let's say Philips Hue, you might get ads on Amazon or whatever. Philips Hue uses a hub and spoke model essentially in most cases, yeah. So the hub essentially communicates to, hub is what has IPv4, your IP connectivity, your IP capability. The light bulbs themselves need not necessarily have, in the case of Philips Hue, have IP access. So in those cases you use something called Z-Wave. Those are all Z-Wave or Zigbee. These are all gigahertz ranges. You need more throughput in some applications, so you use Z-Wave. In some cases your Wipro, your Cisco lights, those connect directly to your Wi-Fi router. Those have IP capability. They use something called ESP8266, like that's a microcontroller with an IP stack embedded right within. So in that case, there's Wi-Fi is essentially your transport layer. Now you will come across, you can go deeper into that communication stack, but for the sake of time, let's move on. You have your processing. So now we are talking from the sensing side. So our soil moisture sensor sends the soil moisture, send it over this LoRa to say the pump house or whatever, contains a Raspberry Pi or a small computer that can receive LoRa signals and transported it to whatever AWS, IOT or GCP, Google Cloud or whatever it is. Now you need to process that data. You need to accept that message, ingest it, store it for later retrieval, and your application essentially is what do you need to do with that data. So your standard action plans. If say the farmer set a rule saying that if the soil moisture level goes below a certain percentage, turn on your pump house or solenoids or whatever. So that can be one application logic. On the business front, say if you want to take some kind of business logic. So a lot of IoT solutions get marketed similar to SaaS, software as a service. So say if you want to put some kind of rate limiting, or if you want to put the user behind a paywall, all of those business logic comes under the business line. That's why it's not as relevant when you talk about the core technology. So since I explained this, I think that can be sort of understood. Let's move into, this is like a basic IoT system based on the AWS stack. So you can, talking in terms of cloud providers, most cloud providers have an IoT solution, but everything is getting consolidated towards AWS. Google recently closed down their IoT offering. Azure is rumored to close down soon. It's a rumor, nothing confirmed, but AWS is pretty much thriving because they have the entire infrastructure to run Alexa. They can keep it good because IoT is a very tough problem. There's a lot of resources involved. In most cases, the cloud providers are making a loss on it, so they have very little incentive to keep it running. And consolidation happens to the largest players in this space. It's AWS. So you have your IoT core, which is essentially where most of these things happen. If you want to get started, or just out of curiosity, if you want to tinker with some things, you can get started with AWS IoT core. Anybody familiar with Arduino here? Okay. So Arduino is sort of like an abstracted programming language specific for electronics. That's essentially the easiest way to get started with most of these things. Arduino itself, if you're talking about Arduino Uno with an Ethernet connectivity or something, it's very tough to get connected with this because Arduino itself does not have the processing capability to negotiate the security. But anything from a Raspberry Pi upwards, you can definitely connect to this, or even ESP8266 you can connect to this. AWS has this thing called a device shadow. It essentially reflects what your physical state is. So if your soil moisture sensor connected to that microcontroller is sending data to AWS, AWS maintains a copy of the last received message. So in case you want to do some analytics or operations on it, you can query the shadow device to retrieve what the last state of that device was. There are several machine learning pipelines within the AWS stack. Machine learning is not my area of expertise, but you can essentially connect, say, Lambda functions to that. To serverless or not to serverless is a debate in and of its own entirely. But all of those are design considerations and architecture considerations. AWS pretty much has a product for each and everything that you can think of. And data exchange to your external systems. So say you want to use SNS, secure notification service, to send a push message to a farmer. All of that can be done within this stack. It's just a brief overview. On the other side you have IoT Greengrass. That's like a general purpose operating system. So one thing about IoT is it's literally a distributed system in the very essence of the word. Once that product sort of leaves your factory premises, you have very little control over it unless you want to do a recall and then do some kind of replacement for your customer. Once the software is flashed and it leaves your premises, it's literally out there. You can't basically go into your server room and do an upgrade, or you can't do that similar to how your IT department handles this thing. So there a concept called FOTA comes in, firmware over the air. So you put in certain logic that allows your company to securely put some kind of firmware within some temporary memory, reboot the device, and flashes the latest version of the firmware. So IoT Greengrass, AWS IoT Greengrass again provides certain abstractions because you have diverse hardware. So hardware that's compliant with Greengrass, you can have certain abstractions that you can work with to efficiently and effectively get things out the door fast with peace of mind. So this is sort of the architecture that I've mentioned. Whatever happens in the backend for IoT is super niche. It does not really make sense for me to cover a specific IoT architecture here because with every client that I've worked with, the architecture differs a lot. So this is again a generic view of things. So you have your sensor and actuator that I mentioned there. So let's take the pump house example itself. Moisture sensor connected to microcontroller, connected to pump house over LoRa, as I mentioned here. So that's that first part, LoRa radio. Edge gateway, cloud gateway, I'll explain in a minute. Went to that business logic, application logic. It fired a signal back saying the soil is too dry, turn on the pump. The signal sort of goes back down the line, and then your actuator comes. Actuator does actuation, as in it influences the environment. Sensors perceive the environment, and actuators influence the environment in some capacity. So that can be similar to a relay, which is like an electromagnetic switch, closes a circuit, turns on the pump.
These are flows synchronous or asynchronous?
Asynchronous. difference between edge gateway and cloud gateway, this is, since I have a lot of architects in the room, I want to sort of drill down this terminology because that is the biggest confusion that happens whenever we are talking with a client. Because sometimes people just say gateway, and they'll use gateway in either of these situations, and then it's up to us to sort of understand what their infrastructure is actually talking about. So everything in the sort of like the back end of things, or within your business logic side of things, is the cloud gateway. So when you sign up with AWS IoT, your IoT core will give you an endpoint, an FQDN, a fully qualified domain name, that you can use to connect that. So that's a point of ingress as in accepting data for your whatever your IoT system is. That can be considered a cloud gateway. It's hosted by someone else. Edge gateway is whatever is sort of you can consider physically on-prem. So let's say in the case of Philips Hue, you have a hub. That hub can be considered an edge gateway. So if it's like a hub and spoke model, or a star topology, you have your peripheral devices connected to that hub, which is what has your IP stack connecting to the cloud gateway. Now this sort of abstraction can be happened. So this kind of goes for a toss when you're talking about your Wipro or Cisco bulbs or whatever, when the MCU itself is communicating to whatever cloud gateway that is, right? So edge is closer to your actual sensor, cloud is closer to your actual cloud infrastructure. Now once the data reaches the cloud gateway, now you need to do something with it. That's where you come up with your aggregator or stream processor. So let's say, so I'm assuming everyone here is familiar with HTTP, right? Now HTTP cannot be directly used in IoT because of certain design considerations like the power consumption, the fact that both devices have to be online all the time, or at least during the point of communication. So your WebSockets, service events, those things generally do not work very well in this concept. We use something else called MQTT, Message Queuing Telemetry Transport. So that's like a pub/sub model. So you have a central message broker to which all of your clients publish and subscribe, publish to and subscribe from. So MQTT has this concept of topics. So let's say your light bulbs have one specific topic, or you can have hierarchical topics as well. And AWS of course has their own structure of things. From there it can essentially split the data stream into whatever business logic components that are required and treat each device differently as necessary. So that's also where, say, certain action items that can happen. For example, let's say your device sends a heartbeat. So this was actually an interesting point of concern for one of our clients. They had a smart home system, so smart locks, smart thermostats, etc. connected to a hub, connected to their cloud gateway. Hub is the edge gateway, connected to the cloud gateway, and all of this happening over here. The hub was sending a heartbeat every 5 minutes. We were doing a scale testing for them starting from 10,000 devices. They had around 100,000 in production. Their sales forecast was 600,000. So we wanted to validate that their backend can handle it. So we basically simulate that first part of things and figure out how the backend behaves architecturally. Are there any changes? Are there any drawbacks? Are there any design considerations or changes that have to be made? So that certain issues only manifest when you reach a very large scale. So what ended up happening is that heartbeat that happened at 5-minute intervals is what was causing their entire system to break. So this screen itself can be split into several things. You have your admin logic to enroll certain devices. You have analytics itself to get insights from the data. Your business logic, like I mentioned, whatever rate limiting or whatever that you need to implement. Focus areas here. In what is the security system from your edge gateway to the cloud gateway? How can you secure the data? Because this you mean? Yeah. Okay. So by definition, it sort of has to be exposed. The one endpoint has to be exposed. Similar to how your endpoints are exposed. But what we do here is we use a protocol called MQTTS. So that implements TLS underneath. There's also public key, private key system. So for example, if you work with AWS IOT, you can, that's the first point here, device provisioning or enrollment. So security, with security in mind, you need to provision devices into your system. So it creates a public key, private key pair. That's the most common thing. So that gets embedded into the firmware during manufacturing when the firmware is flashed. And that's what generally is used to connect to your broker. Okay. But for development, you can even use user ID, password. Mosquito MQTT brokers version 5 and above have quite diverse means of connecting to its security. But certificates are the certificate CA authority or usual stuff. This is the standard there. Yeah, so device provisioning, Azure kind of led the, kind of had a break, was sort of like a pioneer in this space until recently we have this product called Azure Sphere, wherein during the manufacturing of the device itself, they had certain fingerprints installed there. So even your dev kits, once it's attached to a Microsoft device, you couldn't resell it, you couldn't just transfer it to another developer. It's permanently attached to your Azure account. So device provisioning, basically at the factory itself, you need to include certain things within your firmware that are going to be used downstream. Configurations, of course, can be changed and updated. Any rolling token logic that you have, also you need to implement some kind of a fetching mechanism right then and there. Real-time data processing. This is there in certain sort of traditional software systems as well, but in the case of IoT, think of a situation where you have your fingerprint lock that can be considered an IoT system. Say you entered your, like you scanned your fingerprint, that processing and validation took, say, your server was busy with some other synchronous task, the response came, say, 5 minutes later. Or maybe in the meantime you got validated and you got in itself. The door will randomly open, right? So that real-time aspect, so you need to invalidate certain tokens. So those kind of design considerations kind of need to be made when you're in an IoT environment as well. Certain cases you need to know when to invalidate data, when to accept data in a timely manner. In a lot of cases, the database used are time series databases, so timescale DB, Quest DB, something along those lines. Power and bandwidth management. So LoRa, for example, is a slightly lower frequency, lower throughput model. So in some cases, this is just plain text, right? You don't need a lot of capacity going through the network. So you can basically design your system around whatever budget that you need in terms of power and bandwidth. Device experience. This is the biggest pain point that I still have. So I have a bunch of Wipro lights in my flat. Up until a recent time, basically, if the internet goes, I had no control over my lights. I found a solution to it. That was another different talk entirely called self-hosted IoT, wherein you can sort of hack your devices into using a local server instead of a remote server. So that's your device experience. You need to consider how your device behaves in the system and design your architecture accordingly. And like I mentioned, literally distributed systems. You need to factor in what you're going to do, what modifications you're going to do, if your system basically has some kind of an issue down the line, or how you're going to handle updates. Challenges that we often face in the IoT sector. Security, privacy, interoperability. These are like very interesting challenges that are still being addressed. There are solutions to it that are acceptable enough, but ongoing developments in the field are happening. Interoperability being one of the greatest challenges, because there are business incentives to ensure that Wipro's devices don't work with Cisco's devices, or Google's devices don't work with Apple's devices, and things like that. It has gotten much better recently because of certain things that I will show in the coming slides. Development challenges, like I mentioned, the diverse skill set required. So hardware people and software people sort of need to go hand in hand. So you need strict definitions of interfaces between the hardware and the software teams. So let's say if you're dealing with JSON is quite inefficient here. Usually A lot of industry standards will use protobufs or some kind of interface pattern with quite rigid type filtering to ensure that all the teams are sort of in sync there. Data filtering and optimization, there might be, like I mentioned, a lot of irrelevant data and oversampling can happen. Collecting too much information that might not be, because data is expensive, right? Once you start storing stuff in AWS, you can understand how your costs start surging. I'm sure there might be a lot of stories here of people who have burned their hands with AWS costs. So that's data filtering and optimization. Protobuf is one example of optimizations that if like people generally start off by sending JSON payloads, but eventually you find that understand how much data optimization you can ensure by using some interface like protobufs or Arrow. Network and infrastructure constraints. Essentially, there are certain things. For example, your design requires you to use LoRa and the bandwidth constraints that it has. So, or maybe IP addresses, for example. If one particular vendor has this insistence or design consideration that each device will have its own IPv4 address, your IPv4 block is limited. You kind of need to design around it so that you can sort of stick within the allowed limits that are present in the code. And Murphy's law, basically everything that can go wrong will go wrong in some capacity, so you need to sort of account to best case scenarios and sort of account for failure rates, because even in hardware when you manufacture, it's a fun fact that I read that you actually pay around 4x or 8x of what your television costs, because the pricing is sort of decided budgeting in failure rates. Similarly, you sort of need to account for certain failures that are bound to happen in this.
Minimum is 2.5x.
Yeah. Now the hope, like I mentioned, standardization. A lot of industry collaborations have happened. Matter is one such protocol I'll show you here. Because a lot of waste happens. I still remember one of the things that sort of made me critical of IoT is there was this bulb that I used that was Bluetooth based. They just removed that app from the Play Store, iOS Store one fine day. And there was no way to control that device at all. This is probably around 4 years, 5 years back. Now that's e-waste basically. I can't turn on that bulb, or that bulb just keeps blinking. There's nothing you can do about it. That's e-waste. Nothing good comes out of it. There have been initiatives taken to bring in standardization or like sort of pass these business incentives and growing together. So Amazon, Google, all of these big players have sort of come across with that's essentially industry collaboration as well. Edge and fog computing. Like I mentioned, a lot of these things, a lot of these business logic or application logic need not go all the way to the cloud. This is a residue from that initial hype phase where connect everything to the internet or connect everything to the cloud. A lot of data need not go all the way to the cloud. If you set a rule saying that my light has to turn on at 6 a.m., that logic need not reside in the cloud. That can stay in your edge gateway itself, and that rule can be executed there. What if I have a power outage or like an internet outage in the middle of the night? I still want to wake up on time, right? So, edge computing, fog computing paradigms are being installed into IoT systems wherein you are sort of decentralizing that logic. And in the age of Web3, we can see how all of this is further going to evolve with distributed application processing and things like that. Simulated devices, this has been a gap in the field. Basically, how do you test that your system can handle a very large scale? That's basically what IoTify has been trying to solve there. So a fleet management system, before you deploy it, can it handle 1 million devices or scale? So there's no way to actually test that because you can't have a hardware test bed of 1 million devices, right? So you have simulated devices.
How are you creating this simulation?
It's a JavaScript based modeling in mind that we have made. I can explain offline. So Matter, this is one of the biggest happening things in the IoT space right now. A lot of interesting job opportunities coming here of people who have visibility into this stack. So this has big players behind it: Amazon, Apple, Google, your Nordic Semiconductors. You have your like everything from hardware manufacturing levels to, you can see, Alexa, Samsung. Samsung is actually one of the pioneers in the IoT space. They sort of bootstrap the whole MQTT project and everything. And significant contributions. So this entire stack is sort of it's open source. So here you have your standard LAN protocol 802.11. That is low power personal area network, low PAN. You have Bluetooth. There's also a Zigbee Z-Wave. This is 5 GHz communication wherein you need slightly larger throughput. You have Wi-Fi. Thread is another protocol that's pioneered by Google. All of those have that fit into this system. Zigbee is mentioned here, but what's more popular is something called Z-Wave. It's an open source version of Zigbee. So that's essentially where, so even at the application layer, you have meshing involved by default. So your devices can sort of form a very large network by interlinking with itself. So how do you get started? So Raspberry Pi, this is the board that's mentioned here. There's a lot of shortage and stuff going on. You can look for Raspberry Pi alternatives, or even just start off with your Linux machine, connect to AWS IoT or connect to Azure IoT. Home Assistant is an interesting project. This is how I self-host in my IoT services. There's another talk called Self-Hosted IoT. You can look it up on YouTube. ESP Home is if you want to flash a microcontroller, tinker around with things yourself. There's an interesting demo I did where you can create your own security camera, and all of the logic is written in YAML. So yeah. Why do we have so many?
Why do we need Zigbee? Why Google has to unite everything?
No, there is. So the problem is backwards. These exist. Now we have to figure out what to do with them. we have to get them to work well with each other.
LoRa is what? Is a protocol or it's?
LoRa fits into this layer.
So it's a thread is something different. It's not.
Yeah. So the difference there. So I am not very much like a hardcore L2 guy. But essentially the difference happens wherein the radio frequencies that happen. For example, Wi-Fi is 2.5 GHz and 5 GHz. LoRa is 433 MHz. Thread is also 433 MHz to the best of my knowledge. Zigbee is gigahertz again. Bluetooth is again gigahertz, 2.4 GHz.
Different protocols or whatever transport there, and within Bluetooth also there are 1, 2, 3, 4.
Yeah.
These are coming.
So all of those differences come in where how the connection handshakes take place, how those are established. Basically how, for example, how you pair Bluetooth is not the way that how you connect Wi-Fi, right?
Maybe the capacity is more.
Capacity throughput, yes, of course.
Range.
But the handshaking,
Range also.
range also, of course. So as it's an inverse law, right? The higher frequency you go, the lower the range is. If your 5 GHz Wi-Fi will not have the same range as 2.4 GHz, but 5 GHz better throughput than 2.4 GHz. Those are trade-offs.
What is Matter?
Matter is this open standard that's essentially coming. So if you it's also being adopted. I think Apple HomeKit, Apple in their October announcement essentially showed some of their HomeKit additions to this. So Matter is a layer of abstraction where it gives a lot of libraries that you can use to interface with all of these. So it's open source. So that's the entire novelty about this. As in you are having an interoperability layer. So things that you buy from Amazon, say suppose Wipro comes up with a partnership with Amazon. But I use mostly Apple devices in my home. Now, there have been cases in the industry where I can't get Apple to work with Wipro at all because business incentives. Now, this is sort of like a abstraction layer or interoperability layer that is coming out in the industry, wherein you can essentially develop with these libraries and the mesh logic that it provides. There's a standard provisioning system and everything. So your hub can be from one company, your appliance can be from another company, your cloud provider can be from another company, and you can control everything with Google or Siri, Google Assistant or Siri or whatever. So I'm running a bit out of time. There's a small quiz as well along the QA. So yeah, that's basically the talk.
One question I have.
Yeah.
Since you
you are a practitioner of IoT,
Yeah.
there is a latest trend in containerization of embedded platforms where you can update your software.
I know Sony is working on it.
Orchestration and all those things.
Yeah.
So what is your take on that? Like what is your experience?
Distributed processing.
Is there any need for containerization in embedded platforms?
Yeah, there is, because there's a lot of processing power that stays idle, right? There's a lot of processing power that essentially stays idle, that's not required essentially. But so for example, when some kind of an appliance is on standby, you can use that compute power for something else. Or
upgrade of the software.
yeah, of course. All of your container principles also apply to those kind of systems. So you can sort of pull and run. You can do rolling updates.
Do you see need, since you are a practitioner in this field?
Yeah.
Do you see need for that?
It's an interesting concept. I think, yeah, there can be a good application of that. The thing is, a lot of this is not necessary, right? There's a lot of business choices that you make are quite nuanced in terms of that there would be certain applications where that is necessary. But then there's a lot of cases where that just becomes an overhead. Virtualization and containerization always has overhead compared to bare metal. But that's not even like a design consideration when you're talking about servers, right? You can't run your Node.js application on bare metal and it's just not practical. You can, of course, but it's not practical. So those are trade-offs. So there will definitely be an application where that's necessary.
So I would like to share my experience on that containerization. Basically, I am working on an IoT project. In that, multiple companies are working.
One second.
Yeah, so there are multiple companies are working on that. So I prefer containerization because the deployment is easier when multiple companies are working and they will be using different tools, and even some companies are using Python for simulation testing and all those things. They have different C++ tool chains also. So if containerization present, then yeah, the deployment will be easier. That it will come with its own tool chain and its own system.
Of course. But are you talking about that on the hardware level? Are you talking about containerization on the edge or the hardware level?
Raspberry Pi.
Yeah.
Yeah, in the IoT hub system. It could
In
be
the IoT hub
Raspberry Pi.
system?
Yeah,
Okay.
it could be IoT hub, Raspberry. We are using.
So you're running containers on that, say container.
Yeah, we are using.
You run a container D,
Exactly.
container D or something on it.
No, not container D. We are
Docker.
using Podman, Docker.
Podman.
Yeah.
Oh, okay. So that's interesting.
Yeah, and it's production level software where it has been developed from 2014, and the first version released on 2021 in all the Volkswagen product line, and from 2022 for 2028 we have one more project which will be in Docker.
Is this what sector is this? IIoT?
It's an automotive.
Automotive. So this is running in the containers are running in the car, essentially.
Exactly.
Oh, that's interesting.
And one more question I also have.
Yeah.
You have been telling about the LoRa and Wi-Fi. So is that like the sensor you are reading through that frequency, LoRa frequency range, and then you are transporting this to cloud through Wi-Fi? Or how?
Yeah. So I think there is a bit of bias that I have coming from an electronics background. When I talk about sensor, I talk about like silicon, whatever the electronic part of whatever that is. So whereas when you talk about sensor, you might be talking about that electronics plus the microcontroller. When I talk about sensor at its lowest form, I'm talking about something that can get data from the environment. That's it. So that can be a voltage level or something. Then you have a microcontroller, and now that microcontroller needs to get that data somehow to the edge gateway.
Yeah.
Right. So let's consider your ADAS, your vehicle driver assistance system, is detecting a rapidly accelerating vehicle coming from the back. Now you have CAN bus, or CAN bus is used in automotive, right? And say hypothetically that your compute is in the front, near your dashboard or something. Now you have a wiring harness to transport this CAN bus, right? Now CAN bus is an application layer protocol. You have your differential signaling and everything, but forget that for a moment. So you have, suppose there's no wiring harness, you need to get the signal from the back of the car to the front of the car. Now, what is the physical layer that you're going to use to link both of these?
Okay, understood.
So LoRa consists of multiple things. One is the base 433 megahertz layer and whatever pulse code modulation or whatever that you're doing to get data through that. And it also handles the negotiation of the master client from say the sensor is the client, ADAS is the master. How do you negotiate that? All of that comes in the LoRa
So
stack.
it transmits the telemetry message.
Correct.
Thank you.
He raised his hand.
There is this thing called TR369. It's
Sounds familiar.
it's like a sister to TR069 that is used in like routers and stuff.
Right,
So
right.
the ISP can push configuration directly
Right,
into the
right,
router
yeah.
with TR069. So TR369 is also by the same industry standard body, broadband aligned. How would that compare to Matter? Would you have any insights into that TR369?
No, that's an entirely different domain entirely because that comes under FOTA, firmware over the air.
Yeah,
Right?
TR069 can do firmware
Okay.
over the air, but it also does configuration. Like if you want, the ISP wants that everyone should no longer be able to do WPS
Okay.
or something. It can just push a setting to
Okay.
disable that, or it can change your Wi-Fi password. Nowadays, Airtel has this thing where
Yeah,
you are
in
changing
the
your
phone you can-
Wi-Fi password from your app, and it goes to Airtel, and it gets back through TR069.
Correct.
So that is for network devices, TR069. There's TR369 for IoT.
Okay.
I'm not that good with it, but I wanted to
I
get your
have
opinion.
not checked TR369 spec and how it fits into Matter. Actually, Matter is slowly just gaining industry adoption. So it's still in its early stage. So most of the clients that we are talking to or people that I've worked with are not on a Matter stack. Right. And it's going to hit consumer IoT first. It's just like this is more relevant, but I'm not very sure.
What is the language of development? Usually for the application development part, but
Yeah.
which is the language we are using, for example, Node.js or Java or something like that?
So that's pretty much diverse, right? Like whatever system that you want. Sorry, the question was what is the language of development? So let's say your traditional software system can have quite diverse components, right? Similarly, in the hardware side, in most cases it's C, C#, whatever you usually write your firmwares in. On the server side, it can be Lambda based. Lambda supports whatever Golang, Rust, Node.js, all of that stack. There are companies with Ruby on Rails. Yeah, it's quite diverse. Depends on it.
What is it of databases to use?
Database timescaling is quite popular whenever it comes to time series data. This is an abstraction on top. It's an overlay on top of Postgres. We personally use something called QuestDB, which is also using Postgres underneath. Yeah, that also kind of depends on your use case. Sorry?
Which time series database?
Timescale DB.
NoSQL databases are also used.
NoSQL databases, again, that depends on the application, right? If it's like rapid polling of sensor data, it has to be heavily time bound. But whereas if it's transactional, say these many people got into a building or this entity has this characteristic, then NoSQL makes more sense. But for normal time series data, just keep putting it into SQL. Any other questions? Yes, sir.
Yeah, so I have a general question. So I bought a bike in 2010.
Okay.
So the bike has a so when I do the left and right indicators,
Yeah.
so when it turns it off automatically. There was a cool thing about that when I bought I never realized it. So when I start using it, I see it's really useful and then it was making me that feel comfortable on this one. But recent days we bought a bike, scooters, so which doesn't have these features. So is there any cost cutting the companies are thinking there is a good feature that we promoted, it will be more useful for nowadays, right?
Yeah.
So what is there anything like immediately companies are ignoring it or is it cost effective?
It's a design oversight basically, right? Because it's taken for granted. The question was the turn indicators that you usually have. It's a de facto feature in your bike or your car. After you turn, it goes off. Whereas in recent electric scooters, that is, according to his personal experience, that feature is missing. So that there might be some electronic cutoff that would have been going off after the steering turns physically. That physical component might have been removed. They might might have put it into the software feature backlog. Might come with a
Still it's running.
firmware of-
Still is running it.
and
But
for-
because now we are paying little more on the bikes, but still there's certain features are not there.
Yeah, definitely. One. Yeah.
It's a follow-up on the programming language.
Yeah.
So like, for system programming, normally people use C or C++ now, but at least on the server side, like Go is quite getting popularity, like Kubernetes from many kind of things have been written in usage. That is the case with IoT also.
A lot of
like
it.
microcontroller being written in Go, or Go or Rust.
Yeah, so I saw an abstraction where you can use Golang to write stuff for microcontrollers, but I'm not sure how developed that. Last time I checked was in 2020, early 2022, but I don't know how much it developed since then. That toolchain, people who use the bare bones C toolchain, it's a skill gap, right? People going into that side is slightly lesser, so that toolchain sort of persists. I think Rust has more potential in there. A lot of interesting applications of Rust at low level is coming up, and that has a lot of features that are relevant to that, right? But then the learning curve for Rust is quite steep, so
Zig is also making
yeah.
errors.
I didn't say Python. Python.
Circuit Python, so Python itself is a bit heavy because it's an interpreted language, right? Yeah, so Python, JavaScript and all is interpreted, so you need to have a node engine or at least a V8 engine to interpret JavaScript or Python, whatever. But Circuit Python is like a very trimmed down version that usually runs on, say, Cortex. ARM microcontrollers, I'm sure people are familiar with. There's something called ARM Cortex, which is used for embedded systems. So Circuit Python can be used for yeah, but Raspberry Pi is like on the higher end of edge computing. Raspberry Pi is a very powerful machine. You can, yeah.
Yeah, in the context of MQTT,
Yeah.
so like can I understand like broker needs to be connected to the internet and subscriber that could be
Not exactly. The both need to be connected to the internet. So whatever your cloud gateway is, that might be the point of contact of your broker. So consider the broker as the always on service. It's like saying, can I visit a website without internet? Your client also, your phone also needs internet, server also needs internet. But the difference is, there's sort of two-way communication established there. So your client can basically subscribe to a topic. Whenever some new data comes to that topic, the server will notify the client of that data. Now there is also an added set of features called QoS, quality of service. Depending on what configuration that you say, suppose your phone is hypothetically using MQTT and it's gone through a tunnel or whatever. When you re-emerge from that tunnel and re-establish connection with the server, if you use the same client ID, the server will publish whatever data that you missed that came in during that time.
Okay, so when you were giving the example of large scale,
Yeah.
so in that case, like all the devices might not have internet connection. So which
MQTT is not used there.
Okay, so what protocol will be used there?
No, that can be normal pubs. Basically, whatever, so similar to whatever data exchange that you're using within your internal systems, right? So if that LoRa suite itself usually has publish and subscribe methods, or you can do raw data communication there as well.
Okay, so what protocol can be used in that case?
Then the LoRa stack itself has.
So that means that in Bluetooth and Wi-Fi,
Sorry?
Bluetooth and Wi-Fi, this comes under the LoRa's.
Yeah. So Bluetooth, for example, you can do serial communication over Bluetooth. There's that raw data transfer, your raw datagram model that happens within Bluetooth. Similarly, there is methods within the stack to establish communication there like that. I can explain a bit more offline. I think I'm out of time.
Last question.
Last.
So, how can you handle that for edge, what you call edge node,
Yeah.
or edge gateway? It is a single point of failure, right? So, how can you handle it?
So that's sort of why you use something like AWS. You kind of hope that they kind of ensure high availability for. So is DNS a single point of failure? DNS is one of the most, if you look at the architecture of DNS, it's actually a very fascinating way how how chaos is sort of bringing together maximum uptime. Like a lot of network outages and failures have been caused by DNS, but like those are sort of exception cases. In the same way, you can have that DNS kind of hand pointed at a load balancer and then handle the ingress separately. So that DNS record. So for example, thomasrob.in is my website. Let's say I have something called mqtt.thomasrob.in. That can be pointed at a load balancer that distributes the connections between several broker pools. There are clustered broker services. I'm forgetting the name. Something that I used like last month. Mosquito is the most common MQTT broker, but there are clustered brokers as well where you can have distributed load balanced ingress, so that your ingress is not the single point of failure. There are also this availability zone concept that things implement, so that your traffic is a bit more distributed across zones.
Solace can be considered as a MQTT broker?
Sorry?
Solace?
Solace sounds familiar. I haven't used it recently.
It's an enterprise person.
Yeah. I'm not sure about this MQTT. Thanks. I have a few stickers here. I thought of distributing it within the talks, but it's just some funny thing. But I'll distribute it during lunch.
You can place it in the table, they can pick it up.
Thank you.
Thank you so much. Token of appreciation for sharing the knowledge with them. And now the lunch is arranged. So let's make one single line. Once you pick up lunch, you can go inside the team rooms, enjoy your lunch.